Hello, welcome back to CPU scheduling algorithms. Here we are going to discuss about shortest job and shortest remaining time first algorithm. They are called SJF and SRT with MCQ questions. First, we'll discuss about what is shortest job first scheduling. So, shortest job first scheduling is one in which the CPU is assigned to a process that has the smallest next CPU burst. So, from this we can understand that it purely depends on the burst time. From the burst time, it will pick the process which is having the smallest time. So here now have an example where they are given four processes P1, P2, P3, P4 with the respective burst times at 6, 8, 7, 3. Here in our problem arrival time has not been given. If arrival time is not given, we have to think that all arrived at time 0. Now let's see how to make the Gantt chart for this. So now having four processes. So first we in the shortest job first, we have to look at the smallest next CPU burst. So out of which is 6, 8, 7, 3, which is at the smallest burst time, 3 is having the smallest, the process with the 3, burst time 3. There is the P4 is having the smallest burst time. Am I right? So to make this, to start with here, start with 0. So process P4. P4 takes 3 units of time. So 3. From 0 to 3 it is P4. Okay, so P4 is over. Now the out of which is the next minimum? 6, 8, 7, 6 is minimum. So I'm going to take P1. How long it takes? It takes the burst time of 6. So 3 plus 6 it will take 9. So 3 plus 6 9. It was taken by the process P1. So now P1 also completed job. Now out of P2 and P3, P3 has 7. So 9 plus 7, I can make it as, 9 plus 7 it is 16. I can make the total time is 16. Till 16, P3 executes. The next time is, the last one, the P3 is over. The last one is P2. The time taken needed is 8. So 16 plus 8, it will take 24. P2. So here P4, which is having the smallest burst time, is first taken to the CPU. Then other processes will be taken in the just you have to take in the ascending order of burst time. As here there is no arrival time, you have to take only the burst time. Now let's calculate how it works. Okay. Now what are the process burst time, wait time, turn time? Burst time is given in the problem. Now let's calculate the wait time. What are the wait time for process P1? For wait time for process P1, it is start time minus arrival time. P1 starts at 3, right? So P1 starts at 3. So starts 3 minus it arrives at 0. So it is 3. For P2, P2 starts at 16. So it is 16 minus 0, 16. Whereas P3, it starts at 9. So 9 minus 0, 9. Whereas P4, it starts immediately at time 0, so 0. So now let us record this wait time. For P1 it is 3, for P2 it is 16, for P3 it is 9, and P4 it is 0. So when you take the turnaround time, it's the sum of burst time plus the wait time. Add both. So I'll get 6 plus 3, 9, 18 plus, 8 plus 16, it is 24, and 7 plus 9, it is 16, and 3 plus 0, 3. Now when you take the average wait time, let us take that sum of this wait time is 3 plus 16 plus 9. So here for summing up, we are going to take this 3, 3, 6, 9 plus 0. So the sum is 19, 19 plus 9, 28. 28. So 28 divided by 4. So we'll get this is the average wait time. So the average wait time is 7 milliseconds. Whereas when you add the turnaround time, here we are having 9 plus 24 plus 16 plus 3. So what will you get? When you add this, we'll get, so we'll get the total is 52. So 52 divided by 4 is 13 milliseconds. So when you take this shortest job first, we are getting the average wait time is 7 milliseconds. This is the average wait time, and average turnaround time is 13 milliseconds. So this is how the shortest job first works. So it just considers only the burst time. Okay, here in this problem we are not having the arrival time. So it arranges the process, allocates the process to the CPU based on the next CPU burst time. This is called a shortest job first scheduling. Now the question is, SJF algorithm is optimal? Yes, because it gives minimum average waiting time for a given set of process. But the question is, how do we determine the length of the next CPU burst? Either we can ask the user or we have to estimate. Yes, of course, we can only able to estimate the length. It should be similar to the previous one. Okay, let's analyze it later. For that, we have to know that, and SJF picks the process with the shortest predicted next CPU burst. It is not given, actual is predicted. Okay, because always we cannot predict what will be the expected burst time for the next process to be coming in the future. Now, SJF is non-preemptive. Once a process start working with CPU, it will not release the CPU until it completes the job. But there is another version called preemptive version of SJF. It is called as shortest remaining time for scheduling, SRTF or SRT. This SRT is a preemptive version of SJF. Now let us just take the example. Here we are having 4 process P1, P2, P3, P4, and we have been given with the arrival time. And the arrival time is given as 8495 for each process. Now let us consider how we are going to have this as for shortest remaining time plus algorithm. That is, it is a preemptive version. So how the preemptive works? So now here the arrival time has been given. So we have to consider working with the arrival time. At time 0 only P1 is here. At time 1 P2 arrives. At time 3 P3 arrives. And time 3 P4 arrives. So each process is arriving at different time slots. Now let's make a Gantt chart. Now let's analyze how the shortest remaining time for scheduling works. We are having the arrival time. So I'm making a Gantt chart is more microscopic like that. We have time slots in 1, 2, 3, 4, 5. Now at time 0, only P1 is there. So there is no competition. P1 is the only process. P1 start its execution. Okay, so now P1 completes 1 unit of time, balance it is having 7. Now at time 1 who arrives? P2 arrives in the queue. P2 is having 4 burst time, P1 is having remaining time is 7. So which is smaller? P2. So now P2 will be picked up. Okay, now at time 2 who enters? P3 enters. Okay, P3 requires 9 whereas P2 completes it requires 3. Now P2 will resume because P3 requires 9. I will pick up only a process which has shortest remaining time. Next one is the P4. At time 3, P4 also joins the ready queue. Now P4 requires 5. It will pick it up 7, 3, 9, 5, which is minimum. 3 is minimum. So P2 will complete its job. Right. So from time unit of 1 to 5. So 1, 2, 3, 4 from 5. 4 units of time, P2 will complete the job. Okay. Now all 3 are remaining. So, where P1 requires 7 units of time, P3 requires 9 and P4 requires 5. So which one is minimum? Yes, P4 is minimum. So P4 is chosen. Now already it starts at 5. It requires 5 burst time. So 5 plus 5, it takes 10. Until 10 milliseconds, P4 completes its job. Next two are there, P1 with 7 and P3 and 9. So which is minimum? 7. Why there is 7? Already out of 8, 1 unit of work has been completed. Okay, 1 millisecond work is completed. So the remaining 7, so it will be taken by P1 till 17. Then P1 also completes. The next one P3. P3 requires 9. So 17 plus 9 till 26. P3 completes its job. Now P3 completes. So this is how the shortest remaining time was scheduled for the preemptive nature. Because why I am calling it as a preemptive? Here P1 starts execution, but P1 didn't complete. But meanwhile, P2 arrives with the shortest remaining time. So there is a context switch where P1 moves from running state to ready state and allowing to P2 from move to ready to running state. So this makes SRT as a preemptive version. Now let's analyze the wait time and everything. How to calculate that? There is a arrival time is given. We have to calculate the wait time, right? For P1. How we are going to calculate the P1? Now let us check having the Gantt chart at the nearby. Now let's analyze what is that P1. For P1, arrival time is 0. What is the start time? It starts at 10. But earlier it starts at 0. So it starts at 0, arrives at 0, one slot. Added with what is the next slot? From 10 to 1, it is in the waiting queue. It is waiting in the ready queue. Already it's running. P1 is running. Meanwhile, for P2, it preempts. So from time slot 1 to time slot 10, P1 is in the ready queue. So this is the waiting time. How we can calculate? When P1 resumes at time 10. So here we are to write as 10 minus 1. P1 completes its job. So 0 plus 10 minus 1, 9. So the wait time is 9. For P2, what is the wait time? P2 arrives at 1 and starts at 1. P2 completes its job. So there is no wait time, 0. What about P3? P3, when it arrives, P3 arrives at time 2. When P3 starts executing at 17. So 17 minus 2. So 15. For P4 arrives at 3. When it starts execution, 5. So 5 minus 3 is 2. So what about the turnaround time? Burst time plus wait time. So 8 plus 9, 17. 4 plus 0, 4. 9 plus 15, 24. And 5 plus 2, 7. So when you take the average wait time, what is the sum of the wait time for all this? 9 plus 0 plus 15 plus 2. So we will get 26 millisecond divided by 4. So the average wait time, I can have the average wait time is 6.5 millisecond. Okay. What about the turnaround time when you add this? 17 plus 7 plus 24 plus 7, 52. 52 divided by 4. So the average turnaround time is 13 millisecond. So this is the performance of your shortest remaining time algorithm. Now let us resume our calculation and compute how we can claim that this is the best algorithm. Now for this, let us analyze the non-preemptive version, that is the shortest job first. Non-preemptive version for the same problem. So we have P1, P2, P3, P4, we have arrival order also. So we are starting the Gantt chart. At time 0 there is only P1. So P1 starts its execution. But it is a non-preemptive. SJF is non-preemptive in nature. So remember that it is non-preemptive. Once it is allocated with CPU, it won't release the CPU until its completion. So even though at time 1 and time 2 and time 3 we are having P2, P3 and P4, but P1 starts execution. How long P1 needs? P1 needs burst time of 8. Am I right? So until the time period of 8. Okay. Until 8 milliseconds, P1 start doing its job. It won't preempt the CPU. So now P1 completes. What about P2, P3, P4? You have 4, 9, 5. Out of which is the minimum one? 4. So now P2 is picked up. So P2 will start with 8 to 4. So it have 12 milliseconds till 12. Then 9 and 5, which is minimum. Shortest job is remaining time is 5. Right? Plus 5 means you have till 17. You have P4. Then at the last P3 will take its own 9. So till 26 you have P6. So now when you calculate the wait time, what will be the wait time and turnaround time for P1? For P1, P2, P3 and P4. P1 starts as 0 and it's 0. So what about the wait time? Wait time is 0. What about this wait time for P2? P2 starts at 8. So 8 it arrives at 1. So it's 7. So 0. So what about the P3? P3 starts at 17 where it arrives at time 2. So it is same 15. What about P4? P4 starts at 12 but it arrives at 3. So it is 9. It will be the total time. So total time will be of total wait time will be 31. When you take 31 divided by 4, the wait time is 7.75 milliseconds. When the wait time is increased, obviously there is an increase in your turnaround time because turnaround time is nothing but wait time plus burst time. Add the burst time. For P1 burst time is 8. So 0 plus 8, 8. For P2 it is 4. 7 plus 4, 11. For P3 is 15 plus 9, 24. And P4, 9 plus 5, 14. So what will you get here? So what you are getting here? So when you add this, we will have 57. So 57 divided by 4, we are getting is 14.25 milliseconds. So this is the average turnaround time. So when we compare this, so this is the preemptive version, this is the non-preemptive version. Preemptive versus non-preemptive. In the preemptive version, I can get the average wait time is 6.5. But the non-preemptive version, it is 7.75. So we can understand this SJF and SRT, shortest remaining time. So average wait time is lesser in your shortest remaining time than your shortest job first. It is non-preemptive version and preemptive version. Preemptive version versus non-preemptive, right? So preemptive scheduling is shortest remaining time, SRT, which gives lesser wait time than your non-preemptive version of your shortest job first. So out of which always the shortest remaining time will have a better performance. But we have to understand that when compared to the SJF, we have more context switch. So at the cost of context switch and overhead, SRT performs better. Let us review some multiple choice questions based on the shortest job and shortest remaining time. In shortest job first scheduling, the next process selected is the one with the highest priority, shortest arrival time, shortest burst time, or shortest wait time. There is nothing to do with the priority. We already discussed that. We are not having anything have a priority here. And shortest arrival time. So we are not bothering about the arrival time. So we only bother about the burst time. So shortest job works based on burst time, not on waiting time. So the answer is SJF schedules the process based on shortest burst time. And shortest remaining time first is non-preemptive version of SJF, preemptive version of SJF based on priorities only, used only in batch systems. And just now we analyzed that shortest job first is the non-preemptive version which will not release the CPU, whereas shortest remaining time when a high priority job, that means when a process with a shortest next CPU burst or shortest remaining times burst time CPU want to have, because a process that comes with a shortest remaining time arrives, there is a need to preempt the currently running job. So it is the preemptive version of SJF. So shortest remaining time is the preemptive version of shortest job first algorithm. In SRTF, a running process is preempted when there is a need for a preemption. A process with a smaller arrival time enters. A process with smaller remaining burst time arrives. A process completes I/O or context switch happens randomly. And let's analyze. A process with smaller arrival time enters. So there is nothing to bother about arrival time because whenever a process arrives, that comes earlier or late, it will be in the ready queue. So SRTF works based on shortest remaining time. So burst time. So it's not arrival time. A process with smaller remaining burst time arrives. Yes, it is based on remaining burst time because it may be already a half run process. So it's a remaining burst time. Yes, let's rule out the other two. Any process completes I/O. If a process completes I/O, where the process will go? The process will move from waiting state to the ready state. Yes, it will move to the ready state. It cannot directly come to the running state. So it's ruled out. A context switch happens randomly. I cannot make a random switchover of jobs in the CPU scheduling based on the parameter. Here SRTF will preempt only based on a remaining burst time of a process. So the answer is a process with smaller remaining burst time arrives. Next question is, which statement is true for shortest remaining time for scheduling? Option A always results in the shortest wait time for each individual process. Option 2 may cause starvation for long process. Cannot be used if processes have different arrival time. Always gives same result as FCFS. So the option A is always result in the shortest waiting time for each process. So here shortest remaining time, this is in shortest wait time for each individual process. No, it's not about wait time. We'll determine the process based on the burst time, right? May cause starvation for long process. Starvation that we'll discuss in detail about priority scheduling. Starvation means waiting for a long time. Okay, here the process is waiting for the CPU for a long time. So what happened? When the shortest remaining time first, a short job comes, the long process is put in the queue for a long time. Am I right? If a process is having a remaining time is 10 and it is waiting, other process arrives with remaining time is 3, 5, 1 like this. Always the previous process are picked up. Whether the process with the 10 remaining time will be wait for a long time. So this is called as may cause starvation for a long process. Cannot be used if processes are different arrival time. No, the previous example we discussed at each and every time a new process may arrive into the queue. I can have a shortest remaining time to analyze because we are not going to have the shortest burst time. We are going to analyze what is the remaining time to complete this. So that option is ruled out. Always gives the same result as FCFS. No, SRTF is best, better, and optimal result producing scheduling algorithm, but only drawback is it may cause starvation for longer process. Yes, so SRTF may result in starvation for longer process. Thank you.